Drawing Lewis diagrams for diatomic molecules. Let's start with an easy one, hydrogen, H2. Once again, we need to figure out how many valence electrons hydrogen has. Each hydrogen has one valence electron times 2, because there are two atoms, gives us 2 valence electrons. Now remember, hydrogen is a little bit different than all the others in that it's not searching for a stable octet. It's stable when it has 2 electrons. So we draw each of our hydrogen atoms and put a bonding pair in between them. That's it. Basically, we've taken care of it because those are the only electrons there are to work with. So each of these hydrogens is content because each one believes that it has a full outer shell with 2 electrons. Let's take a look at another one. Chlorine. Chlorine has 7 valence electrons in each one of its outer shells, and since there are 2 chlorines, that means 14 valence electrons to work with. So we need at least one bonding pair. That is leaving us with 12 electrons to work with, so we can put 6 around each one of the chlorine atoms. And now we want to see if they each have 8 electrons, or feel like they have 8 electrons around them. And yes, they do. Okay. So we would draw that like this. Here's another example that's a little trickier. Oxygen. Oxygen has 6 valence electrons around each atom. So there are 2 atoms, so that's 12 electrons we have to work with. We need at least one bonding pair. That leaves us with 10 electrons. So if we try to put 5 around here, around each of these oxygens, we're left with the scenario that doesn't make either one of them happy. Because with the shared electrons, each of these oxygens only has 7 electrons. Okay, so in order for the atoms to feel like they have 8 electrons each, we're going to have to move these electrons over to here. As a result, each one of the oxygens feels like it has 8 electrons, and what we formed is a double bond. So oxygen actually is, when it's diatomic, is a double bonded molecule. That is, there's a double bond between the 2 atoms of oxygen. And now for the challenger, nitrogen. Nitrogen has 5 valence electrons in the outer shell of each of these atoms, and since there's 2, that gives us 10 valence electrons in total. We try to distribute these equally around the nitrogens. We know we need at least one bonding pair between the 2. That would leave us with 8 more electrons to work with, so we could try distributing them in such a way that there are 4 around each one of these. Now this doesn't really do the trick because each one of these nitrogens now only feels like it has 6 valence electrons, so something else needs to be done. If we rearrange the electrons so that we move one of each of the ones on top over to the space between the nitrogens, that would give us a double bond, and it would leave 1 electron behind, but it still isn't going to give us the correct number of electrons for each one of the atoms because they'll only have 7 each. So we need to do one more little thing. I'm going to have to move one more electron, this one here and this one here, over to the space between the nitrogens. And now what that does is it makes each one of the nitrogens feel like it has 8 electrons. And what we formed here is a triple bond between nitrogens.